Buenas tardes a todos. Eh, una disculpa por la demora, tuvimos algunos problemas técnicos, pero muchas gracias a todos por estar presentes en este martes coloquial. En esta ocasión tenemos el honor de contar con la presencia del doctor Wesley Coelho de Pasqal. Esta presentación va a ser en inglés, entonces please let me introduce you to our guest. Uh, Dr. Coelho holds two engineering degrees, one in industrial engineering and another one in computer engineering. He also holds a master's degree in models and algorithms and for decision supports and a Ph.D. in computer science, both with emphasis on operational research and applied mathematics. Dr. Coelho's interests are mainly on quantum optimization and related application, and he's currently leading the quantum optimization team at Pasqal. His work consists in developing innovative algorithms to extend the field of application of our atom-based quantum computers. So, Dr. Coelho, please, you can start with your presentation.
All right, thank you very much. Bueno, esta presentación tiene que ser en inglés porque no tengo el nivel técnico en español para hablar de esto, de cuántico. Pero por favor, las preguntas en el fin, si quieren hacerlas en español, no hay problema. ¿Vale?
Gracias, doctor.
Bueno, let's switch to English now. And first of all, thank you very much, Juan Carlos and Gerardo Ruiz, for this invitation. I'm very happy to be here with you guys, and sorry about this to be being late here today because classical computers doesn't work too much with me, actually. So yeah, thank you very much for this nice introduction. As you can see my screen, we're going to talk about quantum computing, and I'm trying to give you guys a very gentle introduction to it. So we'll be a very high level. So let's dive into it. So just before going to details about quantum, just a very quick introduction of myself. As Juan Carlos was saying, I have two engineering degrees, one in industrial engineering from Brazil, I'm Brazilian, and the one in computer engineering from France. I also hold a master's degree and a PhD degrees on computer science, more related to applied mathematics, and mostly with the emphasis on operations research, meaning optimization. And about my professional background, well, I've been doing research since my first year in the university back in 2013, so it's more than 10 years now. And I joined Pasqal a little bit more than 3 years now. And it's been like 2 years that I'm leading the quantum optimization team that is composed by physicists, mathematicians, computer scientists, and we are creating algorithms that can be run on our technology, the quantum computers that we are building. So about Pasqal itself, you might not know about us. It's a French company. It's founded by 3 brilliant minds, Georges Olivier, that developed this technology of trapping atoms inside a vacuum chamber. And with his PhD advisor, Antoine Brouwer, that's a guru of quantum computing here in Europe. And with his supervisor, Alain Aspect, who you might know, he won a Nobel Prize 3 years ago and thanks to this discovery that was rewarded with the Nobel Prize, we had this new technology that is the basics of the quantum computers that we are building. So we are building neutral atom-based quantum computers, meaning that we have atoms inside our computers that can make the computation for us. And we have the company was born 6 years ago, and we already have more than 300 people working with us. Almost 80 people holding a PhD degree. And if we merge all the publications that we had so far during our careers, we some more than 400 publications and patents. And we are all over the place here in Europe. We have some antennas in Canada. We have Pasqal, Canada, Pasqal, France, that is the headquarters. And also we have Pasqal, Netherlands, and Saudi Arabia, and Asia, in South Korea. So we are building the full stack solutions, so meaning that we build quantum computers, and we sell those quantum computers, and we also put them in the cloud so people can use them through the cloud. But also we provide algorithms, we provide everything that will be run, that will be used in that algorithm that might solve a problem for a customer. So that's the big picture of us, Pasqal, a French company. But today is not about Pasqal itself. Let's talk a little bit more about quantum computing in general. So here's the agenda for today. We're going to start with a very, very high level quantum computing introduction. As you saw, I'm not a physicist, so I'm going to give you guys a very high level introduction to the quantum physics behind quantum computation. And I'm going to show how it's done with our QPUs, the quantum computers, based on neutral atoms, that is our technology, just to show you guys that it's not magic. It's very accessible, it's very easy to understand, it's very natural. And for sure, we're going to discuss a little bit about today's reality, meaning where we are right now, where we're going to be in 5-10 years from now, and talk a little bit about the myth and the limitation potential of the quantum computing, right? So first of all, what is the quantum computing? So, and why we need and why we are interested in using quantum computers. First of all, is to solve interesting problems, and the most natural problem that we can use the quantum computers on is simulated quantum system, meaning that instead of using classical computers to try to understand how quantum system behavior, it's interesting to use another quantum system to simulate it. So what we do, for example, for drug discovery, for example, or material science, there is a very in atomic level that we have to study those things. It's better if you use another quantum system to simulate it. So it's the most promising application of quantum computers. But also we talk a lot of solving optimization problems in very basic words. Optimization problem is when you have some problems to be solved, you want to optimize some cost function, meaning try to increase your profit or minimize the cost of your production. Meanwhile, you have to respect some technical constraints. So that's the definition of optimization problems. Like, for example, if you want to know the path that Mercado Libre deliver has to do, respecting the time window that all the customers are imposing. So you have to do some optimization problem that you want to minimize the time that the deliver guy will will deliver everything while you respect all the constraints. And also what we have, we're talking, not the hot topic, is the machine learning right now, and then you can merge and make it even hotter, saying quantum machine learning models, so way to introduce quantum computers to enhance some machine learning models and solutions. So that's the main applications. So let's see how it goes, how we can use them so that this kind of problems. So here it's just to show you guys the different types of quantum computers that we have right now. So we have at least 8 main technologies that can be used to build a quantum computer. We have the famous ones, superconducting ones, like those ones from IBM and Google, but also we have our technology based on neutral atoms. And all those names that you can see here are companies that are building quantum computers based on these different technologies. So it's a very interesting landscape for quantum computer right now, because as you can see, all those names that we have here are not labs, are companies building quantum computers. And here in blue, dark blue here, are companies that are software companies. So they don't build quantum computers, but they provide solutions based on other companies' technology to solve clients' problems. So just to show how many different technologies we have and how many companies we have out there right now. So yeah. So just to, before going to details, let's set the bar here and just go through some very important aspects of the quantum computing. So let's go a little bit on the quantum physics itself. So what I'm going to try to do is to be in the high level and always try to do some analogies with the classical world, let's say, right? So what we have, the classical, the main aspects of the quantum mechanics that we going to use to do quantum computing is superposition, decoherence, and entanglement, right? So let's go with superposition right now. So superposition is one of the most important aspect and element of a quantum computer that we use to do quantum computing. So what does it mean is that any quantum particle, like an atom or a photon, we can prepare them in a superposition state, meaning that an atom, for example, can be excited or not, or both, can be excited and not excited at the same time. Is the classical analogy that Schrödinger did with the cat, being in the box, alive and dead at the same time. But I'm not going to go through that example. I'm going to give you guys maybe a easier example doing with flipping coins. So supposing that you have a coin that you flip, while it's being in the air, flipping around, you don't know if that coin is showing heads or tails. In the air, you cannot know, but you might say that, well, if we don't know, they are both heads and tails. So that's the main, before landing in your hand, that flipping coin is in the superposition of being heads and tails. So since we have only two, let's say, states for that coin, we say that we have a 50% of chance of being showing heads and 50% of chance of showing tails for that flipping coin. So that's and at that time, as I was saying, we cannot know if it's heads or tails. So that's why we say that it's both heads and tails. And that's how you have to see the Schrödinger philosophic experiment, saying that the cat is dead and dead and alive at the same time. It's just because before opening the box, you don't know if the cat is alive or dead. So we say the cat is alive and dead at the same time with a 50% of chance. So that's the superposition element of the quantum computing, and it's the basic element of the quantum mechanics. But I think that with the flip coin in the air, knowing that it's just flipping around, you don't know it's tails or heads. That's the concept of superposition. It's just probabilistically saying that it's 50% of being heads and 50% of being tails, and it can be even 1% of chance being heads and 99% of chance of being tails. So you can say it's a superposition of being both. All right. So that's the superposition aspect of the quantum computing. The other one is the decoherence. It means that the quantum particle can collapse into a single state, meaning that depending on the time and the noise that you can add to the system, meaning like humidity or I don't know, some mechanical fields like electronic fields can disturb the system, and then the whole quantum system can collapse and then become a classical system. Collapsing meaning that instead of being in a superposition, like the flipping coin, when you flip the coin in the air, it's in a superposition, but when the coin lands on your hand, that's the classical world interfering in that system, and then the coin will collapse into one single state, heads or coin or tail. Sorry. So once the flipping coin lands on your hand, that's 100% of chance of being showing that side of the coin only. So it collapses to one single state, and that coin will not change that state until we flip it again. Flip it, right? So that's the decoherence is something interfering on the system, and then the quantum system will collapse into a classical one. So that's the landing coin on your hand, just showing just one face. And then now it's the entanglement. Now things get weird. Now it's when for me as mathematician it became a little bit difficult to understand, but let's try to do with the flip coins also. The entanglement on the system is when two particles are correlated, meaning that when you know the state of one particle will behave depending on the behavior of the other, the entangled and correlated particle on the other side. So meaning that everything that happens to one particle will impact directly the other one. And you don't need to know one particle to know what is going to happen to another one. So let's try to do with the flipping coins again. Now we have two flipping coins, and then suppose that you flip, you have the coins A and B, and they are entangled in such a way that you say that every time that the coin A shows heads, the coin B will do the same. And the other way around as well. Every time that A will show the other way, the other face, like heads or tails, the coin B will show the exact same face when it's landed in your hand, back in your hand. So when you flip the coin A, it will be in a superposition of 50% of chance of being heads or 50% of being tails. And that's okay, but once, and you flip B also, but once A lands in your hand, showing like, let's say, tails, that will impact the state of the coin B, and B will land on your hand, back in your hand, showing the exact same face with 100%. So on this type of entanglement, instead of have 4 possible solutions when you flip 2 coins, you have heads, tails, heads, tails, and tails, heads. In this entangled system, you have only 2 possibilities. So you have only heads, or tails. So once A shows its face, B will show the exactly same one at the same time. So that's the entanglement part, and it's the thing that it starts to be very far from the classical world, and I'll try to show how it works on the quantum computing. So let's go back to superposition. When you do use classical computers, everything is about bits, 0 and 1s. So you have a lot of switches, just open and close the gates, so the electrons can pass by, and when it passes by, it's on. When it starts, it's off. So 1 bit on the classical computers can be only 0 or 1. And everything we have in classical computers is always represented by 0 and 1s. This image that you're seeing, my voice that you're hearing through the speakers, everything is about a very fancy combination of 0 and 1s. And in practice, what happens is that once the bit is prepared, it stays in that very single state. So if you prepare it as off or 0, it will remain in that way if you don't apply any other operation on it. And the other hand of the quantum computer, instead of being 0 or 1, what we have is 0 and 1 at the same time. So what we have is a probability of find that qubit, the quantum bit, in a probability of find that qubit in a 0 state, let's say alpha probability, and 1 minus alpha of being 1. So as you can see here, instead of having only 2 possibilities to have a qubit, 0 or 1 as a bit, what we have is an infinite possibilities, like any combination of alpha and 1 minus alpha percent, let's say, to have this qubit. Can be completely on, completely off, can be half and half, can be 80% on and 20% off, the other way around, any combination that you want it to be. So, and then that starts to be a little bit complicated because everything will be about probabilistic. Everything is probabilistic in the quantum computing world. So it's not that, since we don't know if it's 1 or 0, and we say that it's 1 and 0 at the same time. And we're going to see just this next slide, how we can say that it's on or off, because everything in a classical computer world, it's about ones and zeros, and you have to convert quantum bits into classical ones. So that's the coherence part, and then that's the measurement when you apply some physical classical mechanism on the quantum one, will collapse the quantum system into a very single one state. So, but in the classical computer, when you prepare the classical bit like 1 being 1, when you observe it again, let's say 1 hour later or a few lines later on in your code, if you don't apply any other operation on that bit, it will remain the same. It doesn't matter how long or how long you're going to take to look at it back. The same thing is if you prepare it equals to 0, and few lines of your code later, you'll see it again. If you don't apply any operations on it again, it will be 0. Will hold 0 state. So once in the even the bit is not observed, and after observing that classical bit, the bit will not change. The other way around, on the quantum computers, the quantum bit is a little bit more complicated, because you can prepare a quantum bit, a qubit, in a superposition, saying let's prepare it's a half percent of chance of being 1.5%, 50% of being 0, right? And then you say that qubit is in a superposition, so it's 1 and 0 at the same time. But once you want to see what is the value it's holding in the exact time, and that t, for example, you have to observe it. And when you observe it, you apply a classical interference on the quantum system, and then it will collapse. And once you observe it, it will collapse to 1, right? And if you prepare it again, it will collapse in 0. And if you do this several times, it will be exactly as a flipping coin. 50% of the time that you observe, that qubit will be 0, and 50% of the time will be 1. And interesting is that to come back to the superposition, you have to apply the same operation that you applied before observing the qubit. That's the tricky part, because even though the qubit is in the superposition of being 0 and 1, you cannot access that information without observing it. And when you observe it, the qubit, it will collapse into only one single state. And then, so superposition, so we're going to see about the myths about quantum computers. We cannot explore all the possibilities of the same time with the quantum computers, because we cannot access that information without observing it. And then when you observe, you have only one information, not all of them. So that's the coherence. And finally, the entanglement, the weird part of the quantum computing. So let's say on the classical computers, you have a variable a that say that is a binary variable, so can hold 0 or 1. And then you say that a will be 1 minus b. So to know the value of a, you have to know first the value of the variable b, sorry. So if b is equals to 0, when you apply the equation, then a will hold 1. And the other way around, if b is 1, then a will be 0. But we cannot know the value of a without knowing the value of b. So to calculate a in the classical world, what you have to do is to look at the memory slot of that is holding the variable b, see what is written there, and then calculate a. You cannot calculate a without knowing b. That's the classical computer. When you do this correlated 2 bits. On the quantum computer, on the other hand, it's a little bit different. Is when you say that A is equals to 1 minus B, you don't need to know B to know A. That's the weird part. You can look directly to A, and if A is 0, then you can deduce B is equal to 1, and the other way around. So that's the thing that's a little bit complicated to understand on the quantum computer, is that you literally don't need to know B to know the value of A, because they are entangled, and then you just need to look at one variable. So A, for example. In the flippy coin, if you have one flippy coin here in Earth and another one in the moon, they are entangled like this as before, showing always the same phase. When you flip A here and B in the moon, when A is showing heads here in Earth, B will always show heads as well in the moon. So that's the entanglement. They will behave very correlated, right? So that's the main point of the entanglement. So let's go a little bit quicker about how it works on the neutral atoms. So just to show you guys that it's not magic, and we know how to do everything that I just said with neutral atoms. That is the technology that we use to build our quantum computers here at Pasqal. So to create a qubit, we have to have 5 things. You have to identify what is 0 and what is 1 for you in your quantum system. When you see that 1 qubit, what is represent 0 state, what is represent 1 state, to create the binary representation of the information. You have to know how to do the transition between 0 and 1, how to take a 0 qubit, a 0 state qubit, and go to the 1 state qubit with the same qubit. It's strange, but we need to know where the qubits are, because we have floating atoms inside the vacuum chamber. So you have to know where they are to take to do those calculations. You have to know how to do entanglement between those qubits. That's one of the main aspects of the quantum computing. And you have to know how to measure and collapse the system and measure the system being almost 1 state. And almost every single aspect here are correlated. So let's go quickly into the first one. So for us here at Pasqal, we're using rubidium atoms. So what we have inside the vacuum chamber, we can fill the vacuum chamber with millions of atoms inside. And for us, the atoms that are not excited, we say that it's in a 0 state, and an atom that is excited, we say that it's in a 1 state. For us, if you remember in the high school, all the quantum numbers that we had, you see all the orbits that we have. When we say that when the electron is very close to the nucleus, we say that the atom, for us at least, is not excited. And when the electron is very far from the nucleus, we say it's excited. We say this because to be very far from the nucleus, we have to give a lot of energy to that electron to go up to that level of the system. And that's why we say that they are excited. So for us, when you remember the S,P,D layers, for the 0 state, we say that for us, the rubidium atoms is in the 5s. And then for the excited state, we say it's in the 60 or 70s. So that's our quantum number. So the 0 state, it's a very close to the nucleus, and the 1 state is very far with a very high energy. with that atom to be excited. So that's the main 0 and 1 for us is this. An atom is excited or not. Just this. And the other one is we have to address how we do the transition between 0 and 1. For us is with laser beams. What we do is we have lasers that will address locally some qubits or atoms or globally several qubits at the same time. And then depend of the way that you, the frequency and the time that you shine the laser on the qubit, that qubit will go from 1 to 0 or 0 to 1, or do the oscillation between 0 and 1 in a given frequency. So depending of the time that you are measuring the system, will be more likely to be on one state or the 0 state, depend on how you shine the laser on them. So with the laser, we have a lot of lasers at Pasqal, and we use them to, first of all, to excite atoms and bring them back to the 0 state. Another way that we use the lasers at Pasqal is to, I had an animation here, but it's not working, sorry about that. Is the optical tweezers. What we do is with optical tweezers, we can trap the atoms and move them around. And so inside of the vacuum chamber, the atoms are flying around, and then with the optical tweezers, we can trap them. And once they are trapped, we can move them as we want to create a topology that might be better to represent your problem. So that kind of technology, so the laser will do the transition, but also will trap the atoms to make sure that we put them where they should be and not just floating around. So that's interesting because we really can put them, we have some constraints like the minimal distance between two atoms, because for sure we don't want to fuse them, right? And also you have the maximum distance to the center of the vacuum chamber, because you want that atoms to be inside the vacuum chamber to do the calculations. And then once you have them, you can move them around and you can create very nice figures like that one that we had showing the Mona Lisa. And then we can do in 3 dimensions, and yeah. And the other one is the entanglement. That's the exciting part, literally. What we use is the Hildenberg blockade mechanism, saying that when you have an atom, we always trap them into a 0 state. And then when you shine a laser on it, that it will be resonant with the transition between 0 and 1, that atom will be excited. So go to the 1 state, right? But when you have 2 atoms, you do the same. And you shine the laser on them. What you have is 2 atoms excited at the same time, if they are far from each other. But then you can apply the blockade mechanism and then put them close to each other. And then you do the same operation. You shine a laser on them that will be resonant with the transition 0 to 1. And then what you're going to have is a superposition. So you cannot have them in a 1-1 state at the same time, because they are very close to each other and the 2 excited atoms don't like each other. And then you cannot have 2 atoms excited at the same time if they are very close to each other and if the laser that you use to shine them is not powerful enough. So what you have is a superposition of being 0 and 1 and 1 and 0. So you have these 2 superposition states. Every time that you're going to measure that system, you're not going to see that superposition, you're going to see the system collapsed on 1 sigma 1. So you're going to see 1 qubit in a 0 state And if that qubit is in a 0 state, we are sure that the other one will be in 1 state. And the other way around as well. If you take a look on the collapsed qubit on the left and it's excited, we are sure that the second one will be not excited at all. So that's the entanglement, one kind of entanglement that we can have. And for us is the most important one. And finally, how we know on the system, how we measure the system is literally taking photos of the system. What we have is then once the atoms are trapped, we just switch off the traps and the atoms are in free fall. And then we do the operation, shine lasers on them to evolve the system. And then we switch on the tweezers back. And then excited atoms don't like to be trapped and they just go away. And the non-excited atoms will be trapped again. And then when you take the picture, you see the spots that atoms are in the 0 state. And the black spot that you know there was one atom in there, you know that atom just went away and because it was in an excited state. And then you can deduce that atom was in an excited state, and then you can give the value 1 to that state, to that qubit. And then you take a photo, the shining spots will be 0 and the missing spots will be 1. That's how we measure the system. So just a quick recap. So how we identify 0 and 1 state of our technology is just using the ground state and the Rydberg state of the rubidium atom. The addressability 0 to 1 is with laser beams. We have optical tweezers to trap the atoms and move them around to create the topology that you want. And then the entanglement is done using the Rydberg blockade. And just to measure the system, we use this fluorescence imaging, just literally taking photos of the system, right? So I hope that I convinced you guys that it's not magic, the quantum computing. And so let's talk a little bit about what's going on today with in the quantum world, these last few minutes. So first of all, the myths about quantum computing. First of all, a lot of people are saying that quantum computers are faster at every kind of job. It's not true. Quantum computers don't do faster operations than classical computers. It's just that quantum computers do different operations. It's like GPUs and CPUs. GPUs is way slower than CPUs, but if you put an army of GPUs side by side, you can parallelize everything, and then it will become faster than the CPU. But itself, the GPU is slower than CPU. It's the same for the quantum computer. One operation might be slower than the classical one, but since we can do different calculations that classical computers cannot, that's the main point of the quantum computer. And talking about the myths, saying that quantum computer can explore all the possibilities at once, and when you try to solve a problem, is not true, because we cannot access those possibilities at once, because we have to measure the system every time to see, and once you measure, the system will collapse and will become classical. So you have to do the operations, measure, redo the operation, remeasure again, and do this several hundreds, thousands of times, and then create a historical measurement data that will show that 50% of the time that qubit was in a 0 state, and 50% of the time that we measure it, it was in a 1 state. So you have to repeat several times that operation that lasts for less than few microseconds. And about another thing is that quantum computers will replace classical computers. Here at Pasqal, we don't believe in it. We believe that quantum computers will enhance classical ones, exactly as GPUs did with the CPUs. I think that we can manage to separate, to look at what is best for classical computers and just let them to do their job, and what is very difficult to the classical computer, and then we call the quantum computer. So we're not going to replace classical computer, at least for the next 50 years. I don't think so. We're not going to have a quantum computer in our pocket in less than, I don't know, a lot of years from now. And the main one, the quantum computer will end with the encryption, that everything that is encrypted will be, with the quantum computer, we're going to access all the bank accounts with in few seconds. It's not true, again, because first of all, we cannot explore everything with the quantum computer right now. We have a very small resources right now that cannot do what the quantum encryption propose. And that might be the case in 10 years from now. But by then, you will already have a lot of post-quantum encryption methods that are being developed. By then, we are going to have already something that will prevent quantum computers to break your bank account. Don't worry about it. And then ambitions. That one, using quantum computers to do drug discovery and material science research is very promising, because it's literally applying quantum system to do quantum calculations. So that's the best usage of the quantum computers. And I think that will be the first quantum advantage that we're going to see with this type of technology. Another one is solving complex optimization problems. And that's on my team. We are working hard on this to solve very complex optimization problems with quantum computers, along with classical computers, because we think that the hybrid approach is the most promising path to do it. Also, the quantum AI, so just putting together two hot topics, the quantum and the AI. We think that we might see that quantum computers can enhance some AI models. We already saw this in a very small scale here at Pasqal, and in the future it might be the case. And the most ambitious one is the universal quantum computers, because as I was saying before, we have a lot of technologies. Every type of technologies is very good on different types of operations, and have one single quantum computer platform that it's agnostic to the technology behind. Like today, we don't care if your CPU is Intel or AMD. Everything will be run almost exactly as the same. We can create applications that will be run on those kind of chips. And the ambition is to have the same thing for the quantum computers. And finally, the challenges. Just the last 2 minutes, sorry about this. The challenge is the error correction. The quantum computer is very sensitive to everything around it. Even the humidity in the room can add errors to your calculations. The temperature, how empty is your vacuum chamber, everything can be a source of noise in your system that will add an error to your calculations. Also, the scalability, how big we can go with the quantum computers, because the quantum computers, it's huge. Today is the same size of the first the 50s CPUs that we had with Turing. It's huge. It's 2 by 2 by 3 meters cube. It's a huge machine, and the number of qubits that we have in it, it's very small. And to go big will be a very challenge, and we have to go bigger to have a very industrial relevant application to it. And you have to have software development, because having the quantum computer but not having anything running on it, it's useless, right? So we have to develop this. And to do this, we have to have a lot of trained talent, because at Pasqal, for example, we have physicists, computer scientists, mathematicians, biologists, chemistry people doing everything, because it's an interdisciplinary field. And it's very difficult to find people that know a little bit of everything. So what we do, for example, at Pasqal, we take an expert on quantum physics and train them on the optimization side with the mathematics tools. So sorry about rushing up in the end, but I think that I convinced you guys that quantum computer is real and it's not magic at all. And it's ambitious, but we have a lot of challenges to face, but we think that we're going to get there in the near future. Thank you very much.
Thank you. Thank you, Dr. Coelho, for your nice presentation. Now the floor is open for any questions or comments you have here in Zoom or maybe through YouTube. Just 1 second. I have a question as a neophyte in this topic. Exactly what are the main differences between the classical computing and the quantum computing, and what kind of industries can invest in this kind of technology?
Yeah, thank you. Well, the main difference of the classical and the quantum computer, for me, is the operations that we can do on both sides. The classical one is everything about electronic circuits, that it's just gates just flipping 1 to 0, 0 to 1. And then some problems that it's very difficult to use that kind of way to do the calculations, to explore the whole space of solutions that you might have to your problem. With the quantum computer, you cannot explore everything at the same time, but you can evolve your system in such a way that when you measure it, it will always be in the region that is interesting for you. And then, since that operation is fast, but it's not that fast. For example, the CPU right now, the clock rate of the CPU, it's about gigahertz. It's billions of operations per second. The GPU, it's megahertz, so some millions of operations per second. And the quantum computers today, even though each operation takes more or less few nanoseconds, the whole operation the whole algorithm will take, the clock rate will be between hertz and kilohertz. So it's way slower, but you can do different kind of operations. So evolve the system to be, you have to have applications that you might benefit from, have some stochastic solution, meaning that if you run several times your algorithm, you might have different solutions. So, for example, you're not going to use quantum computers to watch a movie, because you don't want that the Garfield movie, the Garfield will be half of the movie dead and half of the movie alive, right? So you don't want to use the quantum computers to do things that cannot be stochastic, like imaging or dealing with sounds. But if your algorithm will benefit from stochastic, like applying Monte Carlo algorithms to solve your problem, do simulations that is probabilistic, quantum computer will help you on this.
Okay, well, thank you. Finally, we have a question here. This question said, um, what do you think that will be the first major milestone or breakthrough that makes quantum computing commercially available?
Right. Well, very good question. I have two answers to this. The second half is the quantum computer is already available. We are already selling quantum computers, mostly to do research. We plug our quantum computers on HPC centers, so researchers can do calculations on it and have data that you could not have with classical computers because you cannot, for example, do this with the classical. And the major and the for me the first breakthrough applications will be related to quantum simulation. Quantum simulation is simulating a quantum system, and using quantum computer to simulate a quantum system, it's it's the way to do because the classical computers cannot do, and we already saw the limitations of it. So drug discovery, material science research will be benefit from it. That's for sure. That will be the first ones. That's is right around the corner already. I hope that I answered your question.
Okay, yes. And we have another question in YouTube. Raul Mora says, thank you for this lecture. The question is, what are the key environmental considerations in developing scalable, hardware capable quantum computing while maintaining sustainable practices?
Very good question. I think that the first thing that we have to deal with is to be, before going with bigger quantum computers, to make sure that the small ones are stable. That it's very difficult to have noiseless quantum computers, meaning that that it is not being interfered by the classical world outside it. That's the main point that we have to do. So we have a lot of research doing error calculation, error correction, and error mitigation strategies to, okay, even though we have some errors on the machine, we can fix it during the process, during the calculations, or afterwards with post-processing. And with the classical computers, we already do this. We have this error mitigation, error correction, the classical computers. It's on the quantum computer, it's a little bit more complicated because if you don't know exactly what is the quantum state of your system, it's a little bit difficult to correct the error because you don't know if there was an error or not sometimes. But sometimes you know, and then you can apply those kind of algorithms. But you have to stabilize a little bit the quantum computer, the small ones to go bigger first, afterwards.
Okay, thank you. Gerardo.
Gracias, Juan Carlos. Yo le voy a hacer la pregunta a Wesley en español.
Sí, claro, por favor.
Porque habla muy bien español. Le quería preguntar a Wesley si nos puede hablar un poquito sobre las patentes que se dan en este tipo de industria, si le podemos llamar así, de la computación cuántica y de las aplicaciones, digamos, más próximas, digamos, que ya están teniendo o que está teniendo esta tecnología, que es esta mezcla de ciencia y tecnología, ¿no? O sea, lo interesante de todo esto es que es esta mezcla de cosas que ha llevado a este campo que, pues, por lo demás se ve todavía amplísimo para crecer mucho, ¿no? pero vamos, en lo inmediato, ¿no? O en lo inmediato. O sea, al patentar algo es porque ese algo ya está en posibilidad o es importante protegerlo porque está en posibilidad de generar utilidades, ¿sí? Es por un lado. Y por el otro lado, si eso es posible, entonces significa que esta tecnología ya seguramente está resolviendo problemas de inmediatos, ¿no? Entonces, si nos puedes ampliar un poquito este panorama, Wesley, por favor.
Sí, claro. Bueno, creo que voy a regresar al inglés porque creo que mi cerebro está en inglés. Bueno, so about patents, we file a lot of patents in the quantum industry. And today, for example, only at Pasqal, we file at least 50 patents a year. It's a lot because it's an emerging technology. It's a very new, any single step, a very single improvement that you can do, it's already a lot on this industry. And then you always want to patent it because even though you cannot use sometimes on your computer, you can sell it to another quantum company. Because today what we have is not, we want to protect everything that we developed. But today we are seeing a movement that quantum computing companies are not seen as competitors per se. Sometimes it's more about partners. For example, Pasqal, where I work, we are partners with IBM. We don't see them as competitors. It's more about a partner, and we try to do things together. But in the future, once you have and one important thing to say is that we are developing a lot of hardware, very advanced hardware, but we also develop new ways to use it. And those new ways to use them can be patentable also. For example, my team, we are developing new ways to use that technology. So if we can place the atoms in such a way that we can do that kind of evolution, we can solve that kind of problem. And this kind of way to think can be patentable. And we do patent it on solutions, application-oriented solutions, not only on hardware. It's not a mathematical formula that we are patenting, but it's more about giving us technical solution for a technical problem. So how to place the atoms in exactly a way that will solve your problem. That's a very technical solution, and then it can be patented. And so everything at Pasqal, for example, we are mainly researchers. We keep that spirit. We try to innovate. We try to create new things every day. And sometimes we have very good results, and then that can be applied to anything in the future. We're going to patent it. And sometimes we have very good negative results showing that that approach will never work. And then we don't patent it, but we let the world know. And then we publish the paper, say we tested, it doesn't work. Here's the proof that it doesn't work, and we publish a paper. In Pasqal, what we do several times is even when you have very good results and we're going to patent things, sometimes we publish a paper on it as also because we want to open source that solution, and then we publish the paper also along with the patent, meaning that okay, we're not going to make a profit out of this, but no one will, so everyone can use it. It's more about the software side that we do this, but yeah, the patent is a routine in a quantum company. It's every year we at Pasqal, as I was saying, it's at least 50 patents a year that we developed, because we are at 300 people working hard every day, and we have brilliant minds in house. So it's, yeah, we get there every week.
Okay, thank you. We have another question here. Someone saying that is that true that quantum computing can be useful in cryptography? And what can be some uses in this field?
The main thing the people trying to argument on this is using the Shor algorithm that can be factorized prime numbers. That is the base of cryptography system. But today we cannot use Shor algorithm to break the key. Because we need a lot of qubits, millions of qubits to do it. And we will not be in the next 10 or 20 years. So another thing, as I was saying during the presentation, is that by then, we are already going to have a post-quantum protocols to prevent this kind of disruption. So maybe you're going to use quantum to do the encryption, and then it will be robust already to the other quantum computers. So in my opinion, don't worry about it. It might be, we might use quantum computers to do it, but for a good purpose, to create new protocols.
Okay. We have another question. Gerardo Ruiz says, thanks for the lecture. Thinking from a business perspective, what impact can we expect in mid and long term from quantum computing applied to IT assisted decision making?
Yeah, I would like very much to have my commercial team here with me to answer this, to give you the precise numbers. But I don't have the precise numbers, but I know that if you integrate the quantum computers to your solution in a hybrid way, meaning that you decompose your problems to do just part of it being in the GPUs, part of it being in the CPUs, and part of it being in the QPUs. First thing, you cannot do worse than that only with GPUs and CPUs if you do the decomposition. And since the quantum computer is fastly being developed, I think that it will be very, very quick to be, when I say quick in the quantum world, it's 5-10 years. We're going to already have some hybrid methods using quantum computers and machine learning methods using GPUs at the same time. But that for sure will be, for example, we have a lot of, one of our clients are from banks or the drug company, like developing new drugs, new meds in the future, using quantum AI. The hybrid stuff can be very interesting. And in my opinion, will be in 5-10 years, you're going to already have very practical things running every day to do this kind of operations. Today, it's in a very early stage, the quantum AI, in my opinion.
Okay. Regarding the previous questions on cryptography, Alejandro Padron in the chat says, but could be broke the cryptography asymmetric? I don't understand.
Yeah, About the asymmetric cryptography, I'm not an expert, but yeah, I don't know if it will be possible today. And if it is going to be possible in the near future, I'm sure that some post-quantum protocols will be already developed by then. Because we already have a lot of people work on it. Just thinking that, okay, yes, Alejandro, maybe you want to add something?
Yes, can I speak?
Yeah, sure.
Yeah.
Well, okay. Quantum computing broke the cryptographic asymmetric. If you have quantum computing with a lot, many qubits, but for example, IBM only has 50 qubits, but they are unstable, and no problem with that. Well, today, today, no problem with that. Maybe the security in computing is only the standard AES, el AES de 256. Ahorita no se va a romper y no tendremos una computadora a la mano.
Sí.
Gracias.
Gracias. Yeah, I think that let's see what's going to happen in the near future. I hope that we can use quantum computer to work on it, but I don't think it will be used to break it in the future.
Thank you. Thank you so much, Alejandro, for your question. We have a quick question from Samantha Garcia. She says, how long do you estimate it will take for quantum computing to become accessible for the general public beyond research institutions and large companies?
Since yesterday, you already have access to them. For example, D-Wave had a very nice politics that is no longer available, but you could have a free account to use the computer to solve your problems with a limited amount of time, jobs on the cloud. For example, our computer is already on the Azure from Microsoft. If you have credits to use the Azure, you can go through this and use our quantum computer through the cloud. We have other ones on the Amazon cloud that you can access them if you have credits. So you can already use them through the cloud. I don't think that it will be very soon that we can buy one to have in your room. It's quite expensive yet, but you can access to it through the cloud already. It's been I'd say more than 5 years now that we can have access to them.
Okay, well, thank you. I think we don't have more questions for now. So I want to thank you, Dr. Wesley Coelho, for this very interesting presentation and your time, of course.
Thank you very much for the invitation. It was a pleasure. And sorry about running out of time. It's already 20 minutes later, but I hope that it was good for the half of the people here, and the other half we don't know.
Perfect. We have a lot of interactions here also in YouTube. So it was a very interesting and fruitful conversation. Thank you so much,
Thank you
Professor.
so much, and see you next time.
See you. Muchas gracias a todos por asistir, a los que nos siguieron en YouTube, a los que nos siguieron aquí a través de Zoom. A todas las personas que están en el ICAT, los invitamos a una presentación sobre plantas útiles en la Reserva Ecológica de la UNAM. Va a iniciar la presentación ahora después de terminar el coloquio. Muchas gracias a todos. Thank you, doctor.
Yes.
Nos vemos pronto. Hasta luego. Provecho. Recuerden hacer su declaración anual.